introduction. Today, I introduce recent advances on the spot device technologies, especially for the pixel technology and Photon-counting architecture. This is a trial of my talk. After brief introduction of the spot and its application, I will introduce three key technologies for the spot applications. One is the pixel size reduction, another is PD enhancement for near-infrared, and the other is high-resolution photon-counting main sensor. Finally, I will summarize my talk and show small the future prospect. Okay, sorry. First, I introduce spot and its applications. Sorry, just wait. Okay, first I would like to explain the very principle and the working operation of the spot. I think that many people in this room knows this, but I have prepared this slide, so I explain this. Okay, first the spot is an abbreviation of single photon avalanche diode, which can detect single photons through charge multiplication. This illustrates the simple circuit diagram for spot. The applied voltage makes the high electric field in the p-n junctions, and high electric field induces charge multiplication, like this. Single electron, and this shows a potential diagram in the p-n junction. Single electron or hole, which is induced by single photon absorption, is multiplied, and large current can be obtained even with a single photon incidence. The charge multiplication is controlled with, the charge multiplication is controlled with quenching circuit. The spot pixel is connected to the power supply via quenching resistor. This figure illustrates IV characteristics for spot pixel. The BVD denotes the breakdown voltage, which represents the minimum voltage necessary to induce a charge multiplication. The spot current increases rapidly with an applied voltage exceeding the breakdown voltage. The difference between the breakdown voltage and the applied voltage is referred to as an excess voltage, Bx. In order to detect a single photon, it is first required to apply the excess voltage, but any current flows until the photon incidence. Once a photon incidence and the charge multiplication occurs, the large current is induced. This large current discharges output node of the spot, and the voltage drops due to the limited current from the power supply, which is regulated by the quenching resistor. The multiplication current is reduced by the voltage drop, resulting in the quenching of the multiplication. Subsequently, the current from the power supply via the quenching resistor recharges the spot at node to its initial voltage. This cycle generated, so this cycle generates a voltage swing at the output node and enabling the detection of a single photon incidence through the voltage pulse detection. In addition, the timing of this voltage pulse output is precisely aligned at the sub-nanosecond level with the photon incidence, so the voltage pulse output with accurate time resolution can be obtained with the spot. The accurate time detection of the single photon incidence can be applied for distance measurement with time of flight. The spot can detect time of flight of the reflected light at the object. The time of flight can be used for automotive LiDAR or augmented reality and so on. Photon counting is another application of the spot. The number of voltage pulses corresponding to the number of incident photons can be counted with the spot. This high quality and high speed imaging is expected with the photon counting application. But for these kind of applications, a challenge of the spot sensor is LiDAR circuit implementation. The LiDAR circuit is needed in each pixel for these applications, in addition to the quenching circuit. Recently, back-illuminated and 3D structure has been developed, and this allows integrating a LiDAR circuit under the pixel. And both high sensitivity and small pixel size have become possible. This is a trend of pixel size from published work in the past 10 years. The spot pixel size has been reduced to improve the spot sensor's performances. Here, in the last 3 years, back-illuminated and stacked technologies are mainly applied for the pixel size reduction, with the reason as I explained before. Here, I show motivations behind shrinking the pixel size. First of all, a small pixel pitch is essential to increase the resolution. In addition to this, in the small pixel, the incident photons can be discriminated even under high photon flux. The single photon detection is failed with consecutive photon incidence to a single pixel before recharging the spot output node. The possibility of consecutive photon incidence is lower in the small pixel pitch than that in the larger pixel. Thus, that small pixel contributes to detect high photon flux. This improves the robustness of depth sensing against ambient light by decreasing the contrast and the high incident of optical power. And also, this expands the dynamic range of detectable illuminance in photon counting sensors. Okay, so today, first I will introduce pixel size reduction technique to 2.5 micrometer. Here I explain a challenge for the pixel size reduction. This figure shows the typical structure of spot pixel. The distance between anode and cathode contact is very close, and electric field at the pixel edge is very high in such small pixel. The high electric field causes the breakdown at the pixel edge, and this increases dark country rate. This unwanted breakdown is called an edge breakdown. To reducing the pixel size, suppression of edge breakdown is important. This is equivalent to manage electric field at the edge of the pixel or avalanche region. Yeah. To prevent edge breakdown, Shimada et al. Have introduced a circular anode design and a small avalanche region in IEEE 2022. This technique increased the distance between the cathode and anode region. He called the distance as the gathering width, and the width has been maintained even in scaled down pixel by this relative optimization. However, it should be noted that the smallest avalanche region and the widest gathering width are not the best to the edge breakdown suppression. He has confirmed the optimal point B, which is 40% reduction of avalanche region size, is the best to reduce the peak electric field in the 3 micrometer pixel. In this figure shows the simulated electric field with various avalanche region size. The sharp increase in peak electric field can be observed, reducing the avalanche region size less than the optimal point B. Point C shows very large electric field at the edge of the cathode contact here. This is because of extension of a depression region to the heavily doped N-type contact. This figure shows cross-section of the reference 6 micrometer pitch pixel, which is published in IEEE 2021, and the developed 3.3, 3.0, and 2.5 micrometer pitch spot. The optimized avalanche region designs are applied for the developed scaled-down pixels. Furthermore, optimized gapless on-chip planes has a gapless on-chip planes is used in order to improve photon sensitivity in such small pixel. This sensitivity is called as a photon detection efficiency, PDE, for the spot. The conventional on-chip lens has a gap like this between the pixel, and it decreases the PDE. The PDE loss is larger in the these small pixels. So for example, in this 2.5 micropitch case, if we use this gap OCL, the fill factor decreases to 64%. To improve this, we apply this gapless on-chip lens, and this increases the fill factor almost 100%, also in such small 2.5 micrometer pitch pixel. This graph shows measured temperature dependence of dark country rate, DCR, for the developed spot pixels. The DCR is counting rate of generated carrier in the spot pixel without photon incidence. The DCR must be reduced to suppress dark noise over the spot sensor. The 3.3 and 3.0 micrometer pixels have better dark country rate than reference 6 micrometer spot due to the scaled down avalanche regions and optimized gathering. 2.5 micrometer spot suffers from an increase in dark country rate because electric field on the gathering region is 10% higher than the 6 micrometer spot. Although we need more effort to reduce the dark country rate in 2.5 micrometer pixel, but this pixel can be effectively applied for time of flight range image sensors, we think, because dark country value under 10,000 curve per second do not severely affect the depth sensing performance. Finally, this graph shows the pixel pitch dependence of peak PDE in the visible light and 940 nanometer in infrared. The developed spot pixel achieved higher peak PDE compared to the reference 6 micrometer spot pixel. These improvements can be attributed to the gapless OCL. The 3.3 micrometer pixel in particular shows an outstanding peak PDE of 82.5% in visible light. Okay. And next, I would like to introduce unique technique to enhance PDE for near infrared. For time of flight application, 940 nanometer wavelength light is mainly used because the ambient light with sunlight is small at this wavelength. However, absorption coefficient for the silicon is low at the 940 nanometer wavelength, thus increasing the sensitivity at 940 nanometer wavelength is important for time of flight applications, as you know. Then in BSI 2023, Fujisaki et al. Have introduced dual diffraction structure to increase near-infrared PDE. The dual diffraction structure consists pyramid surface for diffraction on incident surface and shallow trench for diffraction on the opposite surface. This technology can diffract incident light both on the incident surface and the opposite surface, and the transmission on the opposite surface is reduced. As a result, the optical path in the pixel becomes longer. However, the shallow trench for diffraction induces damage on the silicon surface during the fabrication process. This figure shows the measured dark country rate versus distance between the shallow trench direction to the multiplication region. The dark country rate increases rapidly with a small distance because of the induced damages. For this reason, they optimize shallow trench diffraction design to avoid avalanche region to suppress the dark country rate increasing. In addition, they also introduced 2x2 on-chip lens on a single pixel. The conventional OCR focuses incident light on the center of the pixel, but the focus point is not matched to the shallow trench diffraction layout. So they applied 2x2 OCR focuses, 2x2 OCR. The 2x2 OCR focuses incident light on STD efficiently, and incident light can be scattered sufficiently, as shown in this figure. The combination of the dual diffraction structure and the 2x2 OCR can increase PDE sufficiently. And as a result, the developed structure has achieved 36.5% at 940 nanometer wavelength with 6 micrometer pitch pixel. This enhanced PDE should contribute to improve depth sensing performance in time of flight range image sensor. Okay, next the final topic. Let's go to photon-counting image sensor with 3.36 micrometer pitch pixel. As I explained the principle, a number of incident photons can be counted. Using the triggering pulse, which is induced by incident photons in the spot and ripple counter. We can recognize the brightness with the counted number of the photons with this architecture. The photon-counting image sensor can be realized to connect spot pixel and photon-counting circuits one by one For the photon-counting image sensor, the back-limit stacked structure is appropriate because the counter circuit can stack under the pixel by pixel parallel kappa connections. However, in this architecture, the circuit size, especially the counter circuit size, determines the pixel size. And the circuit size must be reduced for the pixel size reduction. The challenge of the counter circuit size reduction is trade-off with the dynamic range of the photon counting. I and Ota et al. Have tried high dynamic range photon counting image sensor with reducing counter bit in pixel circuit. However, these techniques need additional circuits for high dynamic range in pixel circuit. As a result, the pixel sizes are larger than 6 micrometer, which are 12.24 and 9.6 micrometer, respectively, in this publication. While on the contrary, Takatsuka et al. Have realized 3.36 micrometer pitch pixel circuit in BSI 2023 by moving the HDR circuit and upper counter bit to outside of the in-pixel circuit. This can be achieved with clustered multi-cycle recharging and overflow counting during exposure. Today, I explain the clustered multi-cycle clocked recharging technique. The CMCR technique is based on clocked recharging photon counting. In this architecture, the spot recharging is controlled with synchronized recharging clock. Number of time slots wherein the number of time slots wherein photons are incident once or more is counted with the clocked recharging. This can limit maximal counting frequency and power consumption even under high photon flux condition. In addition, probability of counting photon with one clock period is determined with time cycle of the clock and photon incidence rate. And they demonstrate high dynamic range by applying the clock recharge with combination of 6 different time cycles. These figures shows the counting response and the calculated SNR. The different time cycle can count photons in different illuminances. Illuminances levels as shown with these thin lines. The summation of the counting numbers with all the time cycles can increase the total dynamic range, as depicted with the thick blue lines. In addition, the overlap of illuminance levels counted by the adjacent time cycles can provide monotonic increase of the SNR, even for such HDR response. This slide shows a theoretical and measured count response and SNR with the CMCR technique. 120 dB dynamic range is achieved as depicted with these blue lines. In addition, bright light response can be controlled with the clock setting. In the CMCR technique, the peak SNR can be increased with reducing dynamic range to 80 dB. This is a captured image with CMCR setting of 120 dynamic range or with 150 frames per second frame rate. Okay. Finally, I will summarize my talk. The spot sensor has been developed for time of flight depth sensor and photon counting image sensor. The spot pixel size has been reduced to improve the spot sensor performance in the past 10 years. Back-limited and stack technology contribute to reduce the pixel size. And 3 to 6 megapixel per pixels has been reported with enhancement of PDE and maintaining low DCR. 940 nanometer PDE is improved to 36.5% with 6 megapixel pitch pixel. 3.36 micrometer pitch photon-counting sensor has been reported with competitive characteristics. And I believe the spot pixel size is further reduced and the sensor performance is further improved in the near future. Today, I would like to introduce one example of the key technology to further reducing the pixel size. And the pixel front-end circuit, which is include the quenching circuit or something, is now integrated on the bottom tier in the conventional 3D stacked structure. The pixel front-end circuit is difficult to implement efficiently in a small area together with a readout logic circuit because the circuit typically comprises a high voltage, such as 3-volt transistor for spot control, and thus this decreases the area for the readout circuit. The advanced stacking structure with 2-layer transistor pixel can integrate the pixel front circuit at the second layer on the spot pixel in the top tier. This expands the area of the area for the readout logic circuit implementation in the bottom tier. In addition, it also reduces the output capacitance between the spot and the pixel front circuit. This structure is further pixel size reduction, performance improvement, or new functional sensors, we think. I will present detail of this structure in December IDM 2024. Okay, thank you very much.